Okay, so Anasaya, you're being now recorded. We're recording now this question. So Anasaya has the question here in question 7. So use the lab to assess the following statements are true or false. And the true or false. Okay, a risk ratio and an odds ratio are different names for the same context. So this is obviously false, right? Because a risk ratio basically gives you the ratio between risks, which are the proportion of an event to happen or not, which is the probability of an event to happen or not. And an odds ratio, you basically converted the risk into the odds. So odds and risk are basically inherently different, where basically odds have been transformed of an event to happen over an event not to happen, which basically transforms the risk from the probability from 0 to 1 into a different value, with 1 being no difference in the risk between both groups, whereas then it basically goes from 1 to infinity, essentially, and from 1 towards null for a protective effect, right? So these are inherently different concepts. When we write, then the second question is, when we write, does that make odds and risk ratio? So you particularly, you have indicated that your question was the third part, right? So when we go through the second, when we write our hypothesis test for an odds ratio, a typical null hypothesis is that OR equals 1. This goes hand in hand with what I just mentioned. So you basically have a risk going from 0 to 1, whereas with where you have the event to happen, the probability of an event to happen as the entire success and failure. So you basically get the prevalence of a disease, or the probability of an event to happen over all entries from your variable or from your population, right? So this is basically from 0 to 1, whereas an odds ratio is converted into a probability of an event to happen divided by only the probability of the event not to happen. By that, you basically transform it, and no risk is essentially a 50-50 risk is essentially 1 at this point. So you essentially, you have with an increase in the odds ratio, you basically have an increased odds of that event to happen. With odds ratio smaller than 1, going towards null, you have a smaller risk of an event to happen.
So like in the PowerPoint where you gave the example of, like, let's say you're doing the hypothesis of like 0.25, and then you have to say either one tail, two tail, but so that 0.25 is not really, has nothing to do with the odds ratio. Like your odds ratio is most likely going to be 1.
Exactly. So the odds ratio is a different concept. You're using a regression method at this point, a logistic regression, to essentially derive this odds ratio, or vice versa. You calculate it basically in a way that you're only looking at the probability of an event to happen over the probability of an event not to happen. So by that, you're basically you're getting an entirely different concept. And does that make it clear? So it's not really anymore about 0.25. I'm not sure where that came from. Where did you read the 0.25?
It was like one of like, it was an example problem.
Okay, yeah, so this is a different concept, right? A risk is inherently different. A risk is essentially a probability out of the entire realm of possibilities. So you basically, you have, let's put it that way, you have a risk ratio, an odds ratio. So you have a contingency table, and you have exposure as the rows, and you have occurrence of an event on the columns. And you basically, with the rows, you get for each of these groups, the exposure groups, you get a certain risk, which is essentially the probability of this event to happen. So from the column, let's try to, so you get a risk, and then you have the risk of the event not to happen. In the second column, you get another risk, and relating these two risks as a risk ratio will essentially then relate the risks to each other. But the odds essentially are different, because it's not a risk that you're quantifying. It's not a probability, so to say, it's the odds. And so essentially, when you think about rolling a die, if you have a risk, if you look at it in a probability of 6 to appear on a die when you roll it, you have 1 out of 6, right? But when you look at the odds, you have 1 over 6 over 5 over 6. So you have 1 out of 6 divided by 5 over 6. So this is your odds of an event not to happen. Does that make sense? Does that clarify the question? And then when coming to the third question, so if there is an association between two variables in our two-way table, the expected values will differ from the observed values. So when you think of a contingency table, so you have a 2x2 table, and you can, based on the marginal totals, you can estimate one cell, basically what the expected frequency of that cell is, just by the marginal totals, the marginal proportions. So you can, from the total, you can estimate from row and column the first cell on the left upper right. And based on that, you can, using the marginal totals, you can calculate the other expected values, right? And that was in the lecture.
Yeah, correct. So I remember on when I looked at when we have to do the square for our own in SPSS.
Yes.
And I did the associations and the expected values, and like if the actual count was like 50, the expected would be like 54. So I saw that and like I understood in that sense, but like I didn't really understand like exactly why it happens. Like I understand that it does happen, but like I didn't really understand like why the expected value like differs.
Well, the expected value is different because you calculate it from the marginal totals and from the probability with the probabilities on the marginal totals. On the outside of the table, you have the sums of each, and you're calculating based on both in reference to the overall count within all 4 cells. You can calculate for one particular cell what the probability will be. So this being said, when you're basically using this probability to fill that one cell, you can populate all other cells and you expect a value based on this distribution at hand, just on the marginal totals. By that, you're calculating the expected values. And if the observed values then essentially show a different pattern than what you would expect based on the distribution according to the marginal totals, you have with a chi-squared distribution, you can reject the hypothesis that you expected over the observed are not significantly different. So this is your null hypothesis, right? Expected and observed are the same. If you run this against the chi-squared distribution and your chi-squared value exceeds a certain critical value, you're rejecting your null hypothesis based on the corresponding p-value, right? You have a one unimodal right-skewed distribution, which is the chi-squared distribution, and you're going with a one-sided test towards that distribution of the chi-squared value. If it exceeds a certain value, you're rejecting this null hypothesis, and this is calculated with the chi-squared value that you calculate. So this chi-squared value essentially incorporates the differences between observed and expected, sums them up and divides them by the number of entries, right? According to the formula that was presented to you in the lecture. So the resulting chi-squared value, you're then comparing to this right-skewed unimodal distribution that essentially then allows you to do the hypothesis testing based on this one-sided hypothesis test on the chi-squared distribution. Exceeding this extreme value, this critical value, will allow you to reject your null hypothesis and say that your differences from observed and expected are greater than what you would allow under the null hypothesis. And then essentially you would reject the null hypothesis. And the conclusion and interpretation of the chi-squared value is that now the observed are significantly different from the expected. And thus there is an association between two variables of interest. Does that make it clearer?
Yeah, thank you.
Yeah, okay, great. And then fourth question, we cannot calculate the chi-square test if one of our categorical variable has more than 2 categories. And this is false because essentially the chi-square test can be used for a larger number of variables as well. So you can use this expected versus observed in the same fashion, right? So you basically, if you have, for example, you have 3 entries for the independent variable, so essentially you can then, you need to populate 2 cells. And with these 2 cells, you can fill up the other expected values. And then you're doing the same exercise than with the chi-squared. You use the same equation and you again calculate this difference between observed and expected. And you're basically approaching it in the same fashion. And you're testing this against the same chi-squared distribution. And you do the hypothesis testing against the same chi-squared distribution. Does that make sense? Yeah.
Yeah, it was just like the rest made all sense to me. It was just number 3 was like, I don't know if like the way it was worded, but it was just like it kind of confused me a little.
Mm-hmm. So what did confuse you about it? So essentially what you are seeing is so an expected distribution amongst the 2x2 tables would essentially not suggest an association between 2 variables because it assumes the marginal totals to essentially dictate the distribution, right? So you have a marginal total. Yeah.
Understand like the expected values, like that part I understand. I think it was like the association between the 2 variables. It was more so like I was just kind of confused about like what the association was specifically, or like if it was like just a general like association.
Okay, and association is basically where two variables basically they interact in some shape and form. Let's look, for example, at the simplest example of you have an exposure. Let's say you have a cohort study, right? And you have the frequency of, let's say, patients that are being hospitalized. And the exposure would be something like high blood pressure. So you have on the exposure category, you have high blood pressure and low blood pressure. Then you have on the columns, you have hospitalization, yes, hospitalization, no. So you have a certain count. And now the marginal totals of high blood pressure and hospitalizations basically build your expected value for one cell, for your one left top cell. And based on that, you're basically assuming that the marginal totals are building up equally distributed according to the marginal totals, these cells, and thereby assuming that there's no association. But now you have an association between high blood pressure and hospitalizations. You see now more weight on one of these cells that you wouldn't have seen if you only looked at the expected values. And this basically implies then an association between 2 variables where basically high blood pressure associates with increased risk or odds of hospitalizations. And this difference in the cell between observed and expected, they build up your chi-squared value. So the larger these differences from expected and observed, the larger the chi-squared value. And the more likely you're going to surpass the critical value on the chi-squared distribution.
So the way I kind of interpret that is, so let's say you know that 2 things that you're testing are associated with each other. So like if you know that high blood pressure will lead to an increased risk of like patients being hospitalized, then there's your association, and then you can expect that your expected value is going to differ from your observed.
Correct. Now, vice versa, the observed differs from the expected, right?
Okay.
So, but yeah.
All
but
right.
you're right, yes.
All right, that makes a lot of sense. Thank you.
No, of course, no pleasure. I hope it really makes it clear because it's an important concept moving forward because you will deal a lot with risk and odds ratio. So it's important that this concept is quite intuitive for you. So thank you for asking this question. I think that's great. Any other questions on this, Aya?
No, not from my end. I was just kind of So like when I was doing it and I was trying to like work through the problems, like I feel like I have like a basic understanding of like the Z-stat and like in terms of like figuring it out. I was just wondering like, do you know like where, because I try to like look for like online examples to like practice the Z-stat a little more, but they were all like Z-scores instead, which is like not this, it's like a little different. So I was just wondering, like, do you have like any examples of like C stats that like I could work on just to like for my own self, just to improve on that?
Yeah, absolutely, absolutely. Anything in particular you'd be interested in? A particular research question, a particular?
Not really. I just I just want to practice doing it, like just to get
Okay,
just to like make myself feel a little more comfortable, like getting to the right
absolutely.
answer.
I actually have a very good slide deck from Professor Wharton that I also share, which illustrates a very nice example of a C statistic. I'm actually gonna, would you do me a favor and please post this question to the discussion board? Then I will post as a response that slide deck for you and the others. Is that okay?
Yeah.
Okay, great. Then let's do that. Do it that way. So this slide deck will illustrate a very interesting example comparing cholesterol levels of a sample to cholesterol levels in the US population. And it has very nice figures and graphs, which illustrates this very nicely. So I think this is a good instructive example, and I can also post in addition to that some other examples that I have. Okay.
Question, is there a discussion board for week 5 or should I post it under week 4?
Set statistics was week 4, right? So I think it would be good to post it under the respective discussion board.
Thank you.
Of course, my pleasure. Hello, Heidi, you joined.
Hi, sorry. Yeah, I joined and then I guess I didn't. Anyway, I've been having technical difficulties with my computer all morning. So
okay.
yes, I am here and I am listening. I'm still a little frustrated about some things, and I booked a session with a tutor today at 3:30. So I don't have anything specific for you as it relates to things. But I just like to come here and listen to the presentation and the questions. And Usaya always has great questions. So
yes, she had a very good question. So how comfortable are you with the concept of risk versus odds and risk ratios versus odds ratio?
I guess I'm okay in terms of the concept, right? But like I'm actually pretty good at those things. I haven't done I wrote down the problems in the slides today or in the lectures, but I haven't had a chance to do them. So if you wanted to go over them, I would love to hear more about them.
Which specifically do you mean?
Well, the risk ratio and the odds ratio, right? So I was listening to the lecture today, and they can be very, very different. One, it seems like there's not that much difference, and then on the other one, then you realize there is quite a bit of difference. So yeah, risk ratio and odds ratio.
Okay, can you guide me to a specific?
Yeah, I'm going to try and find the slide. One moment.
Okay,
please.
great.
Yeah.
Always makes it easy. We have only limited amount of time, and I think that would be good.
Yeah, no
we
problem.
Can. Yeah, great. Okay, let me share my screen.
And also, it seems like when I have SPSS open, my computer runs very slowly.
Yeah, SPSS is quite an how should I say?
It
takes a lot of processing times. Okay, so we're looking here at cross tabulations. So I think the 2x2 table at this point in your, I think this is quite intuitive, right? So you see risk differences, relative risks, and absolute risks in the respective groups. That's what I was talking about before. So you have the absolute risks in each group. So that's our total. Then we have the relative risks building actually the risk ratio. Then you have odds ratio. And here you have really the odds success over failure, and that really changes the way you're looking at this. So essentially, when you have here the odds for group 1 and the odds for group 2, you derive group and the odds ratio for both groups. So by that, you're relating the odds over each other. So transforming this from a risk ratio to an odds ratio really changes the interpretation entirely. Although they are, particularly with large numbers, they're quite comparable. But that doesn't mean that they're always comparable. So there are reasons where you rather use odds ratios over risk ratios. But this is also, so odds ratios, we're getting back to it in logistic regression. So it's important as a concept to understand essentially what it means. So here we basically have in large numbers, and when we have rare frequency of successes, then this relative risk is essentially quite comparable to the odds ratio in magnitude. But nevertheless, it's a different concept. Risk difference.
Yeah, it was actually this page that I,
This
one that I thought was really interesting, that the relative risk of 5 and then the relative risk of 1.5, and which exposure would have the worst effect on population health, right? So it's surprising because it's like the 1.5, right? And not the 5, or the opposite.
The worst effect on population health. No, the worst effect is the relative risk of 5, right?
Oh, 5. Okay, got it.
And not the 1.5. So the greater the risk in terms of magnitude, the greater the risk, the greater the effect, the adverse effect on population health. So if it's closer than to 1, this risk is essentially less deviating, less different in magnitude from the unexposed group. So it's, to some extent, it's also, you got to look at it from that angle. So you basically, the interpretation of a relative risk is that the risk in the exposed group is 5 times the risk of the unexposed group.
Right. Okay.
Whereas here, the risk is basically 1.5 times the risk of the unexposed group. So that's the interpretation of this. So if you illustrate this here with smoking, you're basically coming here to relative risks, right? So if you're relating now 0.81 to 0.24 as the reference, you basically come to a relative risk of 0.49. Right, so you pick this versus this, and that's basically how you can quantify the risk of identifying a smoker. So it's more likely to be a smoker when you are in the high school group. So with an undergraduate degree, you're actually less likely to smoke. So this is where this risk ratio smaller than 1 becomes a quote unquote protective effect to the outcome in question. So the idea here is really that when you advance in your education, you're kind of less likely to smoke because you're more likely to be educated about this adverse side effects of smoking. Does that make sense?
Yeah, that makes sense. Perfect sense. I got it backwards. But yeah, that makes sense.
Okay. No, it's also, it's essentially when you look here you see the trends of relative risks. Sorry, Anusaya, did you have a question?
Yeah, I have a follow-up question to that. So the relative risk, it's in proportion to like the high school graduate group, right?
Yes,
so like
yes.
The associate degree, if you were to divide the prevalence for associate by high school, you would get 0.88. So
Yes.
in that case, if you're looking at something else like in a similar structure to this, so with the first group, like let's say the high school graduate group, would that kind of be like the one that gets, I don't know how to say this. Is that the group that kind of like gets divided into, like everything else is divided by that one?
Correct. And I see what you mean. And this is essentially what you're looking at here, right?
Yeah.
So when you calculate the proportion, So you basically, your denominator is basically your reference group. This is what you mean to say, right? So if you divide your prevalence becomes your risk, your group specific risk. And you're dividing whatever your reference group is, this is what you will use in the denominator. So you're taking the undergraduate degree, you're dividing it by your prevalence, your quote unquote risk in the high school graduate group. You basically will get it in reference to your high school group. So if this is, yeah.
If they had asked, like, consider the risk of like a college grad compared to an associate degree, then then your reference group would be the second group.
Exactly. So if you want to reference it to an associate degree, you basically take a graduate degree divided by associate degree. So again, then you would, for example, again, you get a very protective effect because the risk in the graduate degree group is very small compared to the associate degree, where you have like a fifth of all the associate degree group members are basically, it's 1/5 of them is smoking. So it will again be a value smaller than 1. And thereby, again, you have a protective effect of education. That's the interpretation of it. If you would approach it the other way around, which you could also do, you could hypothetically take a graduate degree as the reference, and you would basically look into high school graduate as your group of interest. You would do 0.24 divided by 0.08. By that, you get something in the realm of like 3, and you get a relative risk of 3 that essentially would show that having a lower level of education would be associated with an increased risk ratio, with a 3-fold increased risk of being a smoker.
Thank you.
You're welcome. Does that clarify the question? And the interpretation here for the odds ratios is somewhat comparable, but it is conceptually a different approach to the question, because odds and risk are, as you can see with the magnitude, they're different, right? They're kind of corresponding in magnitude and in the way the odds ratio is pointing, but the magnitude per se is different. That makes the interpretation comparable, but conceptually different. Then we have hypothesis testing. Are there any additional questions with hypothesis testing? With proportions, we're basically having populations and sampling distributions. We do the approximation method, basically estimating, and we have done that already in session 3. We're calculating a standard error of the mean, and we assume that we take like random samples and we get estimates for this proportion based on our samples, which are distributing around mean of means, so the proportion of proportions. And by that, basically, we're relating this to a set distribution, using the set distribution to do hypothesis testing. Then we have a one sample test, which is again going in the same direction. There are some exercises. I don't know, do you have any questions specific to any other of the examples?
Those are the tests that I wrote down. I haven't had a chance to do them.
Okay.
Yeah.
Which test in particular?
Well, the one at the, I think he ends with a test, something at the very, very final slide that you get to, right? Oh, one of the slides. I'm sorry. The one sample hypothesis proportion.
Sample hypothesis proportion.
Yeah, it has like the total number of students and the total number of females. It's from the dean of students.
Wait, hold on a second.
Or students. I can't tell you what slide it is, but
yeah, let us go through it. Let us find it. So the students, proportions, number of information. First of, oh yeah, okay. This one?
That one, yeah.
Okay. Is there a greater proportion of females in the health sciences relative to the general population? So biostats classes are essentially a sample of students majoring in health sciences, number of females, X equals 37. So now, if you want to calculate the proportion from that, you basically need to calculate the proportion of females from the overall number of students, right?
Mhm.
So you have 37 out of 47. That gives you a certain proportion. And now you would use this essentially to do hypothesis testing. When you assume the proportion in the general population to be 50%, so 0.5, which is strictly not true. I think it's a little off from 50%, but I'm not sure anymore in which direction. But essentially, you would do it in the same way, right? So you basically you have a one sample test. You again calculate your P0, which is 37 divided by 47. Then you have your Q0, and your Q0 is 37. No, it's actually 47 minus 37. So this is 10 divided by 47. This is your Q. So you basically you get your proportion of females multiplied by the proportion of non-females divided by the overall count, 47. So that gets you to your standard error. And then essentially you just need to calculate the difference between your proportions of females minus the proportions of the population, which is 0.5, right? This is your P0 divided by the standard error that you just calculated. And that gives you a set score. And with this set score, you can then, by multiplying, so you have the set score, you find the corresponding p-value, but that's a one-sided p-value. You multiply this by 2, you come to the p-value two-sided. Does that make sense?
Yeah.
Yeah? You want to calculate this too, or does it make enough sense?
Well, it makes enough sense for now.
Okay, let's calculate it. So. Let's do this quick. So, okay, let's do an Excel spreadsheet. Let's do 47. Let's do, we have female students, 37. Then we have the non-females. Yeah, but mix more into it. With success and female, but it's male students. Then we have 10, right? Total students is 47. It's 47. So now we have a proportion of this, which is 37 divided by 47. 37 divided by 47. Now we have 10 divided by 47. So this is 21%. Good. So if we are going back to the slides now, we have now to calculate the standard error of the mean. This is P0 multiplied by Q0 divided by N, and then the square root. So essentially we're getting SEM. Wait, let me see a minute. Is this big enough? Is it visible?
Yeah, that's good. Thank you.
Okay, sure. So we have a standard error of the mean, which is now square root equals SQRT is this multiplied by this divided by the total number of students, which is 47, right? This gives us standard error of the mean of 0.06. So now calculating the set statistics. So we have population P is 0.5. So this is what we're testing it to. So now we have standard error of the mean. We're calculating now the set. The set is set equals this minus this brackets, parentheses, divided by the standard error of the mean. This gives us a set of 4.81. And I don't even need to look anymore at this point because a set score of 4.8 is significant by all means, right? Do we agree on that?
Yeah, I'm just, I just tucked my head down for a moment. Let me just take this in.
Okay.
So it's C1, which is the female students divided by the population mean, right?
The female student divided by the population mean.
Right. No, I mean, not the population, sorry, the population.
The sample population, right? So
Yeah, exactly. Yeah, sorry. Go ahead.
It's actually not. It's a female student proportion multiplied by a non-female student proportion divided by the n divided by 47.
Mhm.
And that square root gets you to look at the formula here. This
Right.
is SQRT C1 multiplied by C2 divided by B3.
Right.
This is okay.
It's just
because
the
this
Z,
is this
the
formula.
Z was bothering me. The Z was, I was trying to get to the Z.
Okay. Well, let's do this in the Excel spreadsheet. Just let this sink in. Let this sink in. Because this is how you calculate the standard error of the mean. So you're basically finding this. You're finding this proportion of all proportions, right? So you find this one true proportion that from randomly sampling, you have found now that the average of all these proportions that you have sampled basically builds up the center of your distribution, of your normal distribution. And you assume a variation around that, which essentially is related to the number of your sample size, to that number of people in those repeatedly drawn samples. So you get this distribution, you get this normal distribution.
Mhm.
And this is an estimate of this standard error of these sampled proportions.
Yeah.
And this is what you're using to compare it against your population proportion, which you assume to be 0.5.
Right.
Yeah. All right.
And the Z though, the Z is where I always lose it. So can you go over that, please?
The set?
The
Sure.
yeah, that's the one I always lose it on. So, yeah.
Okay. Okay. So let's go through that example that, wait, let me find this example. Just a second. That's going to take me a little bit to find, but I have a very good slide that I'm going to show you. So this is hypothesis testing. Why do I have this? Wait, I'm stopping sharing right now. I need to go through my stuff to find that slide. But this slide will make it really clear. I very much like this slide a lot. It's actually next slide. Just bear with me for a second, please. Got it. Okay. So this, are you struggling with the set in the context of proportions or just generally with the concept of set, which is what I assume?
The concept of the of the calculations, I believe.
Okay.
Just that whole concept of the Y.
Okay. Okay, sounds good. Okay. So these are slides that Professor Waldron has allowed me to share for teaching. And so this is also an example. This is a very good example for Anusaya, who had a comparable question. So, okay, so we have a null and an alternative hypothesis, right? So our null hypothesis, the mean, the sample mean is equal to the population mean, mu0, right? So the question here at hand is it's actually not blood pressure, it's actually cholesterol. This is a typo. If the cholesterol of smoking males is the same as in the general population, assuming that in the general population, the cholesterol level is 211 milligrams per deciliter, or 100 milliliters, 100 milliliters, 1 deciliter. So let's skip the one-sided. And this is in line with what essentially the slides showed that Professor Johnson presented in the recorded lectures. And so now the idea is that we are finding out, so we have one set value, not a set, not set, not So we have one set value which we are trying to compare our sample mean to. So we have a population mean, 211. Now we have a sample mean of given its population mean given was 211. We have a standard deviation given was 46 milligrams per deciliter. So if we are taking now as a research question, we want to compare 195 to the population mean. We essentially would do that now. So we have 211 population mean and 46 standard deviation. So the set essentially is the X bar, that's our sample mean of 195, minus the population mean of 211. And we're dividing this again by the standard error of the mean. So this is the general set score formula. It will be the same for proportions under the normal approximation and also with the calculation of the set. So we're calculating 195 minus 211, and we're dividing it by the sigma, population standard deviation, divided by the square root of the sample size. Gets us to a set score of minus 1.74. So minus 1.74 is, as we know, 0. So I know this by heart already, but because I've taught the example. But it basically it leads to a p-value of 0.0409. So 0.041, 4.1%. Good.
Yep.
Good. These are the 0.041 here. So this is your proportion of a set smaller than minus 1.74. So this is this probability here. And now at this point, you're not looking anymore. You're not standardizing your population, right? Detach yourself from the thought that you are looking at a population distribution or whatsoever. So now the standardization you're doing with the set score testing and the set score calculation, this is the difference between your individual entry in your sample minus the population mean. So you're creating these differences. So you get, if you sample 25 individuals, like we did here, you're calculating 25 differences from your population mean. And these 25 differences you're really comparing here. And these are the ones that you standardize to your mean difference, right? So you essentially, you characterize this difference. Your mean difference is 0 under the null hypothesis. But you essentially, you want to find, is this sample from the same population? Is this sample mean different than your population mean? And these differences here, that would be under a one-sided hypothesis, that would be definitely in that rejection region. So it would exceed that rejection region. But you have a two-sided test, so you have to multiply it by 2 because you assume it can be either smaller or larger. In a two-sided sample, in the two-sided set test, one sample set test, you essentially assume both sides to be possible. And you quantify the probability on both sides of your distribution. And multiplying this by 2 gets you a two-sided test. Okay? So if it exceeds this entry and it is within that rejection region, your difference, then it is to be rejected. Although if you multiply it by 2, it's greater than 5% alpha. Right? Good. Now, if you go for a one-sided test, and this is where it's getting interesting. So this is the same also when you have 227, which was the second example. It's the same distance, right? Again, you have X bar minus population mean, which is 16 again. So this is 211 minus 195 is 16. 227 minus 211 is also 16. So it will be the same p-value, even if it's larger, right? So now with the one-sided test, it gets a little bit trickier because now you need to basically build your rejection region according to your one-sided hypothesis. And this is where it's getting a little tricky, I have to admit. But you have to look at what is my null hypothesis and what is my alternative hypothesis. So if you want to test whether your sample mean is smaller than your population mean, then your null hypothesis would be that your sample mean is greater than your population mean. So now your rejection region of interest is really the mean smaller than 211. So you're only looking to the left You're ignoring the right side. You're only quantifying the left side. So now you have 195 minus 211 divided by 46 divided by square root of 25 gets you again the minus 1.74, gets you again the 0.041, but this time you don't have to multiply it by 2, right? Now you're rejecting it. Now you're rejecting it because you're not multiplying by 2. On the opposite end, if you are hypothesizing now that your sample mean is actually greater than 211, your null hypothesis is that the sample mean is smaller than 211. So now your rejection region is now everything greater than your alpha, right? So you're looking at this range, everything greater than that. And now you have basically the inverse. You have 1 minus 0.041, right? And now you're not rejecting, obviously. Does that make it a little clearer? I hope it does. I like these slides a lot. I think these are very illustrative and they really illustrate what you're essentially testing.
Yeah.
To really keep these in mind, and I will post those. Anusaya, if you could please kindly post on the discussion board, I will post these slides as a response.
I made a discussion board in a discussion post in week 4.
Okay, great. Thank you. I'll post them there.
Okay, great. That helps a lot. Thank you.
Okay, no, I'm happy to hear that.
Like literally, like Anusaya said, just do it over and over and over again. So it gets in my brain, because it does get in my brain and then it goes out of my brain.
Yeah. No, but it's really, it's doing and doing and doing and practicing.
Okay.
And also suggest, if there's a question and you're basically you're struggling with looking at it and being able to visualize it in your mind, I think it makes sense to kind of draw it out exactly like this.
Yeah. Yeah.
Yeah.
Mm-hmm.
Okay, great. Any other questions? Any other way I can help you?
Not right now.
Not right now. Okay.
I think I have my work cut out for me. Thank you.
Sounds good. Okay, now please, if any further questions, I'll make sure to check the discussion board today and tomorrow very tightly, and make sure to respond to your question very swiftly.
Thank you so much.
You're very welcome. All right, no further question. We can conclude for this week, and we'll see you again next week on Thursday.
Thank you.
All right, thank you. Bye-bye.